right, moving into section 2.4 on infinite limits, I want to first kind of take the opportunity to look at some graphs on rational functions. The most basic ones that we have are the ones that we have here, is 1 over x and 1 over x squared. So if you were to plot some points, you can always do it by a t-chart, plugging values in. Notice that this would end up being an odd function. If I plug in negative x, I would get back the opposite of the original. And I would be an even function if I plug in negative x in here. So basically, this one is going to be symmetric over the origin, and this one is going to be symmetric over the y-axis. So making sure that you know these just as kind of a reference point. So can't divide by 0, so x cannot equal 0. So I'm going to symbolize kind of putting a dashed line here, and we're never going to cross this y equals 0 either. It will never equal 0 because the top will never equal 0. If I plug 1 in there, 1 over 1 is going to give me a 1. If I plug 2 in there, 1 over 2 is a half. If I plug 1/2 in there, I get the value of 2. So what this side looks kind of like is a curve that's just approaching those vertical lines. And I also, over the origin, have the same point. So if 1, 1's a point, then negative 1's a point. And then negative 2, negative 1/2. And negative 1/2, 2 would be points. And so what I get is this as my graph for 1 over x. Now, if I look at 1 over x squared, again, you can do a t-chart if you want. Can't put in 0, 1, 1. If I put 2 in there, I get 1/4. If I put 1/2 in there, then I get a 4. So it looks very similar to what we just had, except for it's just a little bit steeper, I guess you could say, and shallows out a little bit faster. And because it is symmetric over the y-axis, then I have a matching piece over here. Again, we're never going to cross these dashed lines that we have there. Okay, so making sure, hopefully this is somewhat of a review for rational functions. Now, if I look at 1 over x, that would be like the 1 over x plus 2, that would be like the parent function of 1 over x, except for now I have a plus 2 there. That is a horizontal translation where I would be going left by 2. So basically, I'm going to pick this graph up right here and move it over by 2. So what does that look like? Well, here's that new vertical line that we're not going to touch, and we'll define that in just a second. There's the horizontal line. We end up having that 1, 1, the half, and the 2, and I end up getting something that looks like that, as well as when I sketch, I get something that looks like that. Okay? All right, the next one is dealing with a value where I have an x on top. So you'll have an exercise where you have to match some graphs. So if you have an x on top, it's very possible, and actually is possible, that you will have a 0 or an x-intercept. Well, what makes a fraction 0? The top has to be 0. So if I plug a number in there that is 0, then that's where my intercept is going to be. But my domain says here that I can't equal negative 2. So nothing is going to ever be passing here at negative 2. Now from this point, you can plug in values. If you plug in like negative 1, I get negative 1 over 1. So I end up getting this point. If you put in negative 1 and 1/2, you would get a value down in here. So we're just kind of sketching some stuff so you kind of get an idea of what some of those graphs look like. Notice here that I do end up crossing that x-axis. But if you look on the left side here, this looks more like one of those rational functions. If you choose any of these values, say like negative 3. Negative 3 on top and a negative 3 plus 1, or plus 2, excuse me, gives me a negative 1. So that ends up being a positive 3. So I get this value up here. If I put in negative 4 over a negative 4 plus 2, well, that gives me negative 4 over negative 2, which is positive 2. So you could plot some points to figure that out, and so end up here like this. What we're going to end up doing is kind of sketching. That would be what that function kind of looks like. Okay, so when it's not a constant on top, you want to kind of maybe plug some values in. Now, this rational function now has 2 values at which our denominator cannot equal 0. If I factor the bottom and into that difference as squares as an x plus 2 and an x minus 2, that means that there are 2 places at which we cannot have valid values, and that's at 2 and negative 2. So we're going to draw those, what we call vertical asymptotes. Again, we'll define them here in a minute as to what they are. Now here again, here's places where you can plot some points. I would let x equal 0, put 0 in there, and you get a -4, so -1/4. About right there would be my y-intercept. If I put in 1 minus 4 is a -3, so I get -1/3. So I get down here, it's very, very minute. You would have a matching since we are symmetric. What would happen is that you end up, if you keep graphing and graphing, you get something that looks like that. And if you try to choose points to the right of 2, say at 3, if I put 3 squared in there minus 4, that's a 5. So that gives me a 1/5. So I would be up here. What's going to happen is if you kind of plot some of those points, we end up getting this that looks on the outside and this on this side as well. Okay, so this is a symmetric even function, so over the y-axis we would have symmetry. So those are just some food for thought. Again, if they're not ones that are kind of in the basic form of this 1 over x and 1 over x squared, then you end up having to maybe plot some points. But we're going to look at that 1 over x squared graph, okay? And for us to not have to scroll, it was one that looked like this, okay? Some people call that the Atari function. When I was in the classroom with my high school kids, we called that the Atari function because it looked like the Atari symbol. So what is the value as x approaches 0 from the left? Notice what happens, that it keeps going up and up and up and up and up. I'm never going to reach that, but it is reaching a very large number. So we're going to say that that is going to positive infinity. And if I look at x going to 0 from the right, it also keeps going arbitrarily large. So we could also state that that is going to positive infinity. Now, can we ever reach infinity? The answer is no. So that means that these really don't exist, but we do set them equal to plus infinity, or in some cases maybe negative infinity. So technically the limit does not go to a finite number, but since they both go to infinity, the limit from the left and the limit to the right are the same, we can state that the limit as x goes to 0 of f of x equals plus infinity. So these are our limits, or infinite limits as we call them. Limits at infinity would be ones that we end up approaching infinity, and we'll see those in just a second. Okay, so in general, for infinite limits, the dependent variable, the y value, becomes arbitrarily large as the independent variable approaches a finite number. So as we go to 0, we end up kicking out an infinity, okay? Now, looking at limits at infinity, the opposite occurs. The dependent variable approaches a finite number as the independent, or the x value, variable becomes arbitrarily large. Okay? So now, I kind of have a little typo. Your paper, this should be at the end, but mine here on here, it's at the top. So we want to look at this function. What happens as x approaches infinity? What happens as x approaches negative infinity? So again, that 1 over x squared is that Atari function. So that means as I'm approaching positive infinity, as x gets really, 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 really large, way out here, what's happening to this? Well, we're just approaching 0. We're never going to equal 0, but we are approaching 0. So that means that we could say that this limit as it goes to infinity is 0. Likewise, if I'm looking at negative infinity, this function as it goes out to negative infinity, and it gets arbitrarily smaller and smaller and smaller and approaches 0. So this is again where the independent variable gets very, very big and our dependent variable goes to a finite number. Those are what we call limits at infinity. So that'll be kind of the next section. So we're just going to focus on the first kind, those limits that if I end up going to a finite number and then we shoot off to positive or negative infinity as our dependent variable. So suppose that f is a function and it is defined for all x near some a value. And if f of x grows arbitrarily large for all x sufficiently close to but not equal to a, then we can say that the limit as x approaches a of f of x equals infinity. Or we say the limit of f of x as x approaches a is infinity. Now, the other side of that can also occur, that if f of x is negative and grows arbitrarily large, so we're going to negative infinity for all x sufficiently close to but not equal to a, then we can write that the limit as x approaches a of f of x can equal negative infinity, and we state that the limit of f of x as x approaches a is negative infinity. So the thing about this to remember, again, in both cases, even though we say that they're equal to positive infinity and negative infinity, the limit does not exist. Okay? We never can reach infinity, but we can talk about it, okay, in a limit sense. All right, so let's look at this graph and let's answer these questions as we approach 1 and negative 1. So here's the graph of x over x squared minus 1 squared. We want to know what is the limit as x approaches 1. Here's x equaling 1. So what happens as we go to the left? It goes to infinity. What happens as we go to the right? It goes to infinity. Therefore, this is positive infinity. If I look at negative 1, x equaling negative 1, if I approach it from the right, it goes to negative infinity. If I approach it from the left, it goes to negative infinity. Since those two things on the left and right are the same, we can say that that goes to negative infinity. Again, it doesn't exist, but we can say that's the direction that it's going. So let's look at another graph. That was the two-sided limits. We can also just look at one-sided limits and then combine them in the end. So it depends on what's given to you and what you have to find. So let's look at x equaling 1, which is right here. What happens as I approach it from the left? Looks like it's going up, up, up to positive infinity. What happens as I approach 1 from the right on my function? It comes down here and it goes up, up, up. So that also looks like it's plus infinity. Therefore, the limit from the right and the limit from the left are equal, making the two-sided limit a positive infinity. Let's turn our attention to x equaling 2. X equaling 2 from the left means that I'm going way up here as, again, a positive infinity. But now when I approach 2 from the right on that function, we are going down to negative infinity. Therefore, because this limit is different than that limit on the right and the left, this two-sided limit does not exist. Okay? So, in all of these previous examples, there's been a line in our function that's been undefined, okay? This vertical line that we don't cross, that we just approach. And that line, x equal a, is defined to be a vertical asymptote. It's hard to get that spelling on asymptote. It's kind of a funky one, but make sure that you know how to do that. So as a formal definition, a vertical asymptote is a vertical line that is approached by the graph of f as x approaches, a, and for the limits, if the limit as x approaches a of our function is equal to plus or minus infinity, or if the limit as x approaches a from the right of f of x is equal to plus or minus infinity, or if the limit as x approaches a from the left of f of x is equal to plus or minus infinity, then the line x equals a is a vertical asymptote of f. So anytime you get those plus or minus infinities limits, then you end up having a vertical asymptote at a. Okay? All right, so let's look here. Let's see if we can analyze this graph and find any vertical asymptotes. So here's the function. It's all factored out for us. That's nice. We end up looking at x equaling 1 and x equaling 3 and figuring out what's happening. So at x equaling 1, this is a two-sided limit, so we have to look from the left and from the right to make sure from the left it's going up, from the right it's going up. Therefore, this is positive infinity. Now, just what we just saw with the vertical asymptote, if that limit is positive infinity, then that means that a value is a vertical asymptote. Now, in this graph, you don't see it, but it is assumed to be there. Now, let's look at -3 from the left. So look from -3 from the left. -3 from the left goes down. That would be at negative infinity. And here we have the two-sided limit of x going towards 3. So from the left, we know it was negative infinity. From the right, we know that it is positive infinity. And so this limit per se does not exist because one's a plus and one's a minus. If I would have had a plus here, that would have definitely been from the right would be at positive infinity. But because of this guy right here also, we can state that x equaling 3 is also a vertical asymptote. Okay? All right, very good. So that's from graphs, but now here comes the analytic part in which we need to make sure that we can find plus or minus infinities as answers just by plugging values in. So that's what the rest of these exercises are for. So not all the time we see graphs, but we will see some functions a lot of the time. So when plugging a in, there are times when you will get a value. If you get that value, that's its limit, you move on. There are times when you also will get 0 over 0, to which if you get that case, you must have to modify the function by factoring or rationalizing with conjugates to get an answer. And finally, there will be times when you get a number over 0. And these will be the times that your answer for your limit will be plus or minus infinity. So let's talk about what happens when we do that. Let's again first plug a in. If I plug 3 right in here, I get 2 minus 15 all over. Plug 3 right in here. 3 minus 3, and that comes with a negative 13 over 0. Now, you can't divide by 0. So we know that this is going to be a plus or minus infinity answer, but we have to determine which one it is. So here's how we do that. I'm approaching 3 from the right. That means I'm coming from like 6, 5, 4, 3 on the right-hand side. So I'm going to choose a number that's to the right of 3. I just go to the next whole number, which is 4. If I plug 4 in here and subtract 3, what kind of answer do I get? I get a positive 1. Now, I don't care about the 1. I just care about the sign. So that comes into a positive value. Now, here we go. We know the answer is going to be infinity, but we're going to use the signs of integers to determine whether it's plus or minus. So here I have a negative 13. Divide by a positive number. A negative divided by a positive is a negative, and that would be your answer. Okay, so let me review that real quick. I know that was kind of fast. You get a number over 0. Then you pick a number that's to the right of this one. Since we have a plus here, plug it in. What kind of sign do you get? It is a plus. Use your integers signs to get your ultimate sign. So let's try another one. If I plug 3 in here, well, it's the same function, so I should get negative 13 over 0 again. But this time I'm coming from 3 from the left. So from 0, 1, 2, 3, I'm going to pick 2. 2 is to the left of 3. When I plug 2 in here, 2 minus 3 takes on negative values. Therefore, a negative divided by a negative is a positive. And since it's a number over 0, our answer will be at infinity. Okay? Basically, because if you get a number over a very, 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 very small number as it approaches 0, then you get a very large number if that's on the bottom. All right, let's try this one. Actually, we don't really need to try anything. We just need to assess what we just did here from the left and from the right. This one is negative, that one is positive, therefore the two-sided limit of this one does not exist. Now, just because that one doesn't exist doesn't mean that I don't have a vertical asymptote, because I come back here to the one-sided limits and I do have them at infinity, making x equaling 3 a vertical asymptote. Okay? All right. Let's try this guy. If I plug in negative 4 into that function, negative 4 cubed is a negative 64. The opposite of that is positive 64. Negative 4 squared is 16 times 5 is an 80. Minus 6 times a negative 4 becomes a plus 24. All over, throwing in negative 4, I get negative 64, so I get the opposite, which is 64. Negative 4 in here gives me 16 times 4, which is 64. So ultimately, if you add that on top, you get a 168 all over a 0. Hence, we know the answer now is going to be plus or minus infinity, but what kind is that? The top is positive, and what would the bottom take on? Now, if I plug in anything to the right of -4, so remember, that's -3, -2. What kind of answer is close to -4 you're going to get? You don't want to pick like 10. You want to pick something close. That's why I choose like -3. If I plug -3 in here, -3 cubed is -27. The opposite of that would be 27 minus -3 squared is 9 times 4 is 36. I don't care the number of that. I just care that it is negative. Therefore, a positive divided by a negative gives me a negative infinity. Now, because I got negative infinity, that tells me that x equals -4 is a vertical asymptote. So you want to make sure that you note that as well. Now, here, you could actually, if you wanted to, you didn't get 0 over 0, so we didn't have to factor, but nothing says you couldn't factor to make it just a little bit easier on yourself if you didn't want to. Either way works. You get the same answer. All right, let's try this guy. We have 6 from the right of 6. We have x minus 7. Throw 6 in. Minus 7 gives me -1. Throwing 6 in here gives me 0, but I'm going to the right of 6, so I'm going to choose like 7. When I plug 7 minus 6 in here, I get 1. It's a positive answer. The square root of a positive is still going to be positive. Therefore, 1 over 0 gives me infinity. Negative divided by positive is a negative infinity. Hence, x equaling 6 would be a vertical asymptote. But what happens when I go to the left of 6? I still get -1. And when I try to plug 5 in here, 5 minus 6 gives me a -1. But I can't take the square root of a -1. So actually, we can stop at this point. Because if you recall, what makes this valid for its domain means that x minus 6 has to be greater than 0. It can't be equal to 0 because we're in the bottom. So I can only really choose values for this function where x is greater than 6 out of the domain. So because I'm going to the left of 6, this do not exist. It's not even a plus or minus infinity. It does not exist because of the domain. Okay? Because of domain. Okay? All right, very good. Now we get a two-sided limit here with an absolute value, but absolute values are a little bit different. They're a little bit special. When I plug in 1, I get 1 over 0. And when I try to assess, even though it's not the left or the right, doesn't really matter if it's the left or the right, what kind of answers do I always get out of an absolute value? Absolute value is always positive. Therefore, no matter which side that I come from, I'm going to get a plus in the bottom. Number over 0 gives me an answer of infinity. A positive divided by a positive is positive infinity. Therefore, again, here, x equaling 1 would be a vertical asymptote. All right, very good. Let's see what we can get here. This is a function where I have x squared minus 2x all over x squared minus x minus 2. This is my f of x over here. When I try to plug in 2, what do I get? I get 4 minus 4 over 2 squared is 4 minus 2 minus 2. Well, that looks awfully lot like a 0 over 0. If it's a 0 over 0, we better factor. Okay, modify that function. So I'm going to factor the common x out on the top. So take out a common x. On the bottom, it's 2 binomials. Since the last sign is a minus, they are different. So I need an x plus and an x minus. And what do we multiply to get 2 that we subtract to get 1? Better be 2 and 1. Those are the only factors. But I need a minus 2 plus 1 to get this -1 up here. So minus 2 plus 1. Make sure you can factor. That's so important. So what's going to happen? To eliminate that 0 over 0, I end up canceling this out. Now, just because this cancels doesn't mean that there's a vertical asymptote there, just because it's in the bottom. Remember, this cancels out, leaving just a hole. So there's not a vertical asymptote here. There will be a vertical asymptote here at what's left over. So my final function that I'm going to be looking at for these limits is x over x plus 1. All right, so this is our check. Now we really want to find out, okay, what is the limit as x goes to 2 of x all over x plus 1? Well, when I plug in my a value for that, then I'm going to plug in a 2 and get a 2, plug in a 2 down here and get a 3. Therefore, I do get a valid number. No vertical asymptotes at this point. It is x equaling, or excuse me, the limit is equal to 2/3. But when I take the limit as x approaches -1 from the left of x all over x plus 1, Then, when I plug my a in, what do I get? I get a -1 over a 0, and I have to determine, okay, -1 to the left of -1 would be -2. Be careful on your negatives. You might want to try to say 0, but that's to the right, not to the left. So if I choose -2 plus 1, that comes on with a negative number. Therefore, this is going to be positive infinity. Now, with that answer right there, we can already constitute that x equaling -1 is a vertical asymptote. Okay, if you have an answer of plus or minus infinity, it will be a vertical asymptote. All right, now what do I have here? I have here where I'm going to take the limit as x approaches -1 from the right of f of x, which is x, sorry, I'm modifying that, x all over an x plus 1. So if I throw in -1, I get -1 on top and a 0 on bottom. But if I go to the right of -1, I'm going to choose 0 this time. 0 plus 1 gives me a positive answer. Therefore, a negative divided by a positive is a negative infinity, and that would be my final answer for that one. Okay? All right. And our last little problems that we have. I'm just going to mix it up here because we've seen all kinds of different values. Maybe if I can get it to turn. All right, so here we're going to find the limit. So again, first thing we do is plug in a. If we get a number, we're done. If we get a 0 over 0, we probably need to factor or rationalize. If we get a number over 0, that's our plus or minus infinity. So let's see what we get here when we plug 0 in. Well, I get 0 minus 0 over 0. So that's a 0 over 0 case. So I must try to factor this first. No square root in there, so no rationalizing. So what if I factor out, there's a common x squared, that when I take that out, I'm left with x minus 5 over x squared. Well, that's awful beautiful because now I have 2x squareds that are going to cancel themselves out, and I'm just left with the limit as x goes to 0 of x minus 5. Now, once you did that factoring, plug that a value in. So plug 0 in. 0 minus 5 is -5. That's the limit that we have there. Next, let's go as we approach to 2. It's a two-sided limit. If I try to put 2 in there, what happens? If I do 2 squared minus 1 all over 2 squared minus 4 times 2 plus 3. Let's see what we get when we work that out. Well, it's kind of nice on top. We don't get a 0. We get 4 minus 1, which is 3, all over. This becomes 4 minus 8 plus 3. Well, what is that? -4 plus 3 is -1. Aha! Notice here we get a valid number right off the handle whenever we plug a in. That is our limit. Okay, that's again one of the most basic ones. If you get zeros, that's where the problems occur. All right, let's try this guy. If I plug a in, I get 1 minus 5 plus 6 all over 1 minus 1. Well, the top becomes -4 plus 6 is a 2 all over a 0. Notice here, this is the time that I'm going to have plus or minus infinity. I now need to hone in from the right of 1. What sign does this denominator take on? I'm going to pick 2 as the number to the right of 1. Put 2 minus 1 in there. I get a positive number. That positive 2 divided by this positive ends up with a positive infinity answer. So we have done quite a few different things with limits, making sure that you plug a in to start with. But again, it determines if you end up getting a 0 over 0 or a number over 0 as to what you have to do from there. So please make sure you practice those. We will then turn our attention now to limits at infinity. So as x approaches infinity, that will be our next section. So until next time.